One of the research team, Jack Lowrey, will lead the next presentation. Jack investigates ways in which geochemistry of WA's ancient igneous rocks can provide constraints on crustal evolution, finding your next gold deposit, and the relation to lithium systems.
Yes, so I'll be talking to you about how understanding sanukitoid chemistry might be able to help you find your next gold deposit. And it's been a team effort, so I'd like to acknowledge my collaborators, Hugh Smithies, Alicia Verbeeden, Jatindra Satkoda, Nathan Bowman, and a couple of people you might recognise from Geoscience Australia, Dave Champion and Kevin Cassidy. And also a special thanks to Dave Champion in particular for donating around 3,000 samples at the start of this project, which really kicked us off with having a lot of samples that we could analyse for this work. So what is a sanukitoid? So for those of you who aren't familiar, they're essentially hornblende-rich felsic rocks. They're defined chemically by having Mg numbers, which is magnesium to iron ratios, of around 60 at 60 weight % silica. And they also have high nickel and chromium, and these characteristics require that these rocks have got mantle sources. So unlike most felsic rocks, which are crustal melts, these ones have been sourced from mantle sources. They were originally defined by Shari and Hansen and named after sanukitoids, which itself is a high magnesium andesite common in island arcs through Japan, and itself was named after the island of Sanuk. In the Yilgarn, most of the sanukitoids we have are typically calc-alkaline. So you see diorites through to granodiorites, but they do also cross over into the alkaline series. So you'll also see monzonites and quartz monzonites. And we use the term sanukitoid to capture any volcanic equivalents of these rocks as well. Here's a couple of pictures of what they might look like in drill core if you were coming across them in the field. So the pictures in the middle are pretty typical porphyritic rocks, feldspar, amphibole porphyritic rocks that intruding the Kalgoorlie group in the Kalgoorlie-Kambalda region. And the black flag group, which overlies the Kalgoorlie group, is also, broadly speaking, well, the bulk composition of that would also be sanukitoid in terms of its composition. And then just to draw your attention to these, in the bottom left-hand corner, these cognate xenoliths, they're quite diagnostic of what sanukitoids look like. They're basically old portions of more primitive material from earlier magma chambers that have been caught up in these sanukitoid magmas as they're rising up through the crust. So the connection between lamprophyres and sanukitoids and gold itself is not a new idea. There were some pioneering studies from UWA by Nick Rock, Caroline Perring, David Groves and others. They really looked at the lamprophyres and sanukitoids in the Kalgoorlie-Kambalda region. And then there was also a parallel research history going on in other cratons, in particular around the Superior province. So as I mentioned before, Shari and Hansen who coined the term. But also Stern et al., a lot of work by them. More recently, GSWA has done quite a lot of case studies on the black flag group, which is, I suppose, the big sanukitoid example that we would, or the type of sanukitoid example we'd often go to. And their parental magmas, the lamprophyres, so that's work by Wally Witt and Hugh Smithies. And now, more recently, our work's starting to focus on how we make that wealth of research knowledge more accessible to modern explorers, developing new tools to help you find your next gold deposits, hopefully. So how do you know if your granites are sanukitoids? Well, we've released a couple of publications now that try to help you work through this problem. Firstly, you need to classify your rocks or your felsic granitic rocks as belonging to the magnesium-rich felsic group, which is the parental group to the sanukitoids. Previously, these would have been known as the mafic granites in the Geoscience Australia scheme. There's a new record that should be coming out very soon, hopefully in the next month, which has got step-by-step instructions on how to classify your felsic rocks into these groups. There's also an iogas calculation file and some diagrams that accompany it, so you can just load that into your iogas folder and click run, and it'll just calculate them and tell you what kind of rocks you've got according to our scheme. And for people who don't use iogas, we've also put it in as it's accompanied by an Excel template, so you can just cut and paste your data into this template and copy the formulas down, and it'll calculate what kind of, or what geochemical group your samples should be assigned to. So hopefully we'll see that soon. And we're also hoping to discuss with the makers of iogas how to integrate it into future releases, so that hopefully it can come out in a future release. So some of the other more recent work we've been doing is looking at why some sanukitoids are more fertile than others. One of the discrimination diagrams you might have seen is our lanthanum ytterbium, lanthanum neodymium discrimination diagram. And when you plot up all the sanukitoids, they form these two real obvious populations, very clear populations. And the black flag group, we've called them type 1 and type 2, and the black flag group and most of the sanukitoids that are associated with gold deposits in the Yilgarn, they fall into that type 1 category, which is the more shallow trend there. A lot more of the older sanukitoids that we see in the West Yilgarn, and some of the older ones in the Eastern Yilgarn as well, and in the Pilbara, fall in that type 2 category. They comply with all the classification criteria for a sanukitoid, but they don't seem to be quite as genetically related to gold mineralisation as the type 1s. So the two diagrams in the middle are their trace element patterns, mantle normalised trace elements, trace element concentrations. You can see the type 1 sanukitoids at the top there have got much steeper trace element patterns than the type 2 sanukitoids. And the other very clear distinguishing feature is their zirconium-hafnium anomalies. So the type 1 sanukitoids have got much lower zirconium anomalies than the type 2 sanukitoids, which have more mantle-like zirconium and hafnium compared to similarly incompatible rare earth elements. And when you quantify the zirconium anomaly, I've plotted it against magnesium oxide here, and you can see there's very little overlap between the two types of sanukitoids. So that's another way that we can distinguish these two types. So we've got multiple types of sanukitoids, and we think we have multiple ways to form those sanukitoids. So the type 1 sanukitoids we think form when lamprophyric magmas intrude and differentiate within the crust. So they have the type 1 sanukitoids, and the lamprophyres have got very similar trace element characteristics and minor element characteristics. They've both got very high phosphorus, very high lanthanum ytterbium. Their trace element patterns look almost identical. They're both strongly heavy rare earth depleted, and both have those very low zirconium anomalies. And these characteristics, along with the hornblende, suggest very, very wet mantle source regions, and these lead to very, very wet and oxidised magma compositions. So those characteristics are fantastic for transporting gold through the crust. And there's that schematic diagram of how that possibly works there. The type 2 sanukitoids, on the other hand, we think form from melting a more moderately enriched pyroxenitic mantle source, so a less well metasomatised source region, probably a bit of a shallower derived melt as well. They have much lower phosphorus, more moderate lanthanum ytterbium, and flatter heavy rare earths, and as I said before, more mantle-like zirconium anomalies. So they're still hydrated and oxidised magmas. They still contain hornblende, and potentially they are still prospective for gold mineralisation, but we would just say that empirically they appear to be less related to the gold mineralisation in the Yilgarn at least than the type 1 sanukitoids. So where are the type 1 sanukitoids? I've mapped them here in red, the type 1 sanukitoids, and the regular sanukitoids mapped in green there. And you can see that they're located near to greenstone belts and along major structures. That's no surprise really, because they're mantle-derived magmas, so we're going to see them close to these translithospheric structures. But I think the important thing to note about the sanukitoids is that they're showing that you've tapped a very volatile, rich mantle source, unlike the greenstones, which utilise the same structures to come up through the crust. The sanukitoids have really tapped that volatile, rich mantle source region. So if you're looking for gold, I think that's the key point there. So you're in a good place to look for gold if you've got sanukitoids. Obviously, the vast majority of them are in the eastern goldfields, but more recent work that's coming out, a lot of the sampling we've been doing since 2020 has started finding these type 1 sanukitoids in and around gold deposits, at least in the West Yilgarn. So around Boddington and Deflector, Mount Magnet and Kew. And then the other notable place where they're sort of popping up is along that southwest you and me terrain boundary. So we're seeing a cluster of them around Northam there, and then and down at around Katanning. So yeah, interesting stuff, and I think future work's probably going to find that there's a lot more of these type 1 sanukitoids in the West Yilgarn as well.